So you're welcome to part 2 of probability, and let's see a few more concepts about probabilities. And these concepts are essential for understanding quantitative risk assessment. This table shows data of a population composed of 10 animals. 2 attributes are described: sex and sanitary status. We can see that there are 6 females and 4 males. At the same time, there are 6 healthy individuals and 4 sick individuals. So the data from this table could be visualized in that form, and that's what we call a scenario tree. In the first division, you see there are females and males, and in the second division, they are healthy and sick animals. If we add the number of individuals of each group, we see that each one adds up to 10. The result should be equal and to the total number of individuals. Now, if we wanted to calculate the probability of obtaining a female, if we randomly choose an animal from this population, we would have to divide the number of females by the total number of individuals. The probability would be 0.6 or 60%. So the probability of obtaining a sick animal, this case would be 0.4 or 40%. And the probability of a male being a healthy individual, what would that be? It would be equal to 0.3 or 30%. In this tree, we have the absolute numbers of individuals in each node, and we could express that in relative terms as probabilities. So if we randomly choose an individual from this population, how likely would it be that that individual is female? And how likely would it be for that individual to be male? So the likelihood would be 60% for female and 40% being male. And what would be the probability of a female being healthy? So we have 6 females and 3 are healthy. Therefore, the probability is 50%. So all these probabilities here that we see, they are called conditional probabilities. Let's look at the one on the top. The event of being healthy has 50% probability of occurrence only if the individuals are female. And that condition, that is a condition that has to be true, and that is why these are called conditional probabilities. So we have already calculated the probability of an individual being female and healthy by counting the number of individuals with the 2 properties and dividing the result by the total number of individuals. But we can get the same result by multiplying the conditional probabilities of both events. In the same way, the probability of all possible outcomes can be calculated. So observe that by adding all these probabilities, we obtain 1 or 100%. And what does that mean? We obtain 1 or 100%, meaning that effectively those are all possible outcomes, and not all of them being equally probable to occur. These probabilities are actually called joint probabilities. Let's see these concepts in the context of quantitative risk assessment. So here we want to estimate the probability that a person is infected by Salmonella through eating chicken breast. The first thing we need is our scenario tree again. So that is, in this case, there are 3 events. The meat has to be infected by Salmonella. The agent must survive processing, and finally it must survive cooking. If these three events occur and a person eats this chicken breast, he or she will get infected. To find out the first event, to find out the first event, we contacted some experts. Here again, the first event is if the chicken meat is infected with salmonella. So the experts told us that the prevalence of salmonella in chicken carcasses in the main slaughterhouses of this country was about 5%. So what does this mean? So it means that in 95% of the cases, there is no risk, but in 5%, yes, there is a risk. Now the carcasses are subjected to the following process. They are washed and cut. The pieces are packed and then frozen. The probability of salmonella surviving this process was also estimated, and it was found to be 20%. So therefore, in 80% of cases, there is no risk. But in 20%, there is a risk. And now the cooking process. When it's well done, there is no chance for salmonella to survive. And the problem is here that is not everybody cooks chicken breast in the proper way. So for that reason, an average survival of salmonella of 10% was observed in food. Now we have our tree with the correspondent values of probability for each event. And these are conditional probabilities. And we want to know the joint probability. In other words, what is the probability of the three events taking place? And so that again is very simple. Of those, what we do in this case, we find out that it's the product of three conditional probabilities. So the answer to the question is that if these assumptions we have made are correct, a person has 0.1% chance of suffering salmonellosis by eating chicken breast. You can also put this differently. It means that 1 in every 1,000 people eating chicken breast may get infected. So see you soon.